Hi everybody! In this video, we will be doing two challenge problems involving empirical and molecular formulas. The first problem involves a reaction, so we will have to calculate the empirical formula and the molecular formula given the information in this first problem. So let's try it out. So it says 10 grams of a compound with carbon, hydrogen, and oxygen reacts with excess oxygen gas, which means that there will be enough oxygen gas to make sure that all of this is reacted to near completion, and all of this 10 grams of compound will be converted into 14.66 grams of carbon dioxide and 6 grams of water. So in this here, we can clearly see that there will be some sort of conservation of mass going on. So let's split this reaction into its left and right side. On our left side, we have 10.00 grams of a compound containing carbon, hydrogen, and oxygen, and we have an unknown amount of oxygen gas. Now, on our right-hand side, we have 14.66 grams of carbon dioxide and 6.00 grams of water. So how do we go about finding the empirical formula for this mysterious compound? So in our last video, if you remember, if you want to find the empirical formula for a substance, you need to know the ratio of moles in that substance. So for example, a 1:1:1 ratio, for example. But we have to do that for this problem. So we have to find a way to find the number of moles of carbon, hydrogen, and oxygen in this compound. So how would we go about doing that? So let's think about the conservation of mass. If 10 grams of a substance containing C, H, and O transforms into this and this, how can we use the conservation of mass to our advantage? Well, notice that on the left-hand side, all the moles of carbon are located in the CHO compound, while on the right-hand side, all the carbon exists in carbon dioxide. So if we find the total number of moles of carbon on the right-hand side, we will be able to figure out the total moles of carbon on the left-hand side, and since all of the moles of carbon exist in this compound, then we would have thus figured out how many moles of carbon there are, and that's our first step in setting up the ratio between C, H, and O. So let's figure out how many moles of carbon are on the right side in order to find the moles of carbon on the left side. So how do we find the moles of carbon in carbon dioxide? Well, let's try to figure that out. If we know how many moles of carbon dioxide there are, then don't you agree that we could figure out how many moles of carbon there are? Since in one molecule or mole of carbon dioxide, there is one atom or one mole of carbon in it. So we could use this relationship to find the moles of carbon by figuring out the moles of carbon dioxide first. Now we're given the mass of the carbon dioxide, so how do we convert grams of carbon to moles of carbon? Well, molar mass, of course. And how do we find the molar mass of carbon dioxide? Well, we use the periodic table. So on the periodic table, the molar mass of carbon is 12.01, and the molar mass of oxygen is 16.00, rounded to the hundredths place. So let's do that math. So we are going to have, let's see, I'll do it in a different color, 12.01 grams per mole plus 2 times 16.00 grams per mole. And, oh, that looks weird. Let me erase that and let me rewrite that. So now that we have this relationship and you do the math, you get that the molar mass of carbon dioxide is just 44.01 grams per mole. So now that we have the molar mass of carbon dioxide, let's find the moles of carbon dioxide. So let's find the moles of carbon dioxide. So we are going to multiply 14.66 grams times the molar mass. We have to make sure the grams is on the bottom. So 44.01 grams. And on the top, we have, well, a mole. And if you do the math, let me take out my calculator. 14.66 divided by 44.01 is equal to 0.3331 moles of carbon dioxide. So we figured out how many moles of carbon dioxide there are. And we just talked about how 1 mole of carbon dioxide has 1 mole of carbon, since there is 1 atom of carbon in 1 molecule of carbon dioxide. Remember, moles is essentially the same thing as molecules or atoms. It's just a bigger amount. So 1 mole of carbon is in 1 mole of carbon dioxide. So we could write that conversion factor. We could say 1 mole of carbon per 1 mole of carbon dioxide. So we can multiply this conversion factor by this number to get the moles of carbon. So we could do that, I guess down here somewhere. We'll do it down here. 0.3331 moles of carbon dioxide times 1 mole of carbon dioxide per 1 mole of carbon. And when you multiply number by 1, you get the same answer. So our answer for this problem is going to be, let me undo all of that first. It's going to be 0.3331 moles of carbon on both sides of the reaction. So by finding the moles of carbon in carbon dioxide, we definitively figured out the moles of carbon on the left-hand side. And since all of the carbon exists in the compound, we have thus conclusively found the number of moles of carbon in, I guess, this 10.00 gram compound. So let's move on and let me erase all of this and let's look at the water now. So let me do some erasing. Let me erase that too. And let me write 0.3331 moles here for record keeping. So let's now look at something else. So let's write the 14.66 grams of carbon dioxide again. Let's try to figure out an element that only exists in 1 compound for each of them. So in this case, we know that the hydrogen on the left-hand side all comes from this compound, and that's what we want. And we know that all the hydrogen on the right-hand side all comes from the water, because carbon dioxide does not have any hydrogens in it. So now we could find the moles of hydrogen on the right-hand side, and thus find the moles of hydrogen inside this compound, since O2 doesn't have H, so we don't worry about it. So let's find the moles of H in H2O. But first we have to find the moles of H2O. So the molar mass of H2O is 18.02 grams per mole. You could do that by looking at the periodic table. So now we have to convert grams of H2O to moles of H2O. So we would just multiply 6.00 grams times 18.02, and on the top it will be a mole, and on bottom it will be grams. So the grams will cancel out, and we're left with, according to our calculator, 6 divided by 18.02 is 0.333 moles of water. So now we have to find the moles of hydrogen in the water. So how do we do that? Well, we know that for every mole of water, we actually have 2 moles of hydrogen. And why is that? Well, for every molecule of water, we have 2 atoms of hydrogen. So we can translate that into moles and say for every mole of water, we have 2 moles of hydrogen. So now that we've got that and the conversion factor, let's just figure out how many moles of H there are. So I think that we multiply 0.333 moles of H2O times this conversion factor, so moles of H2O on the bottom, and on the top we have 2 moles of H. So the moles of H2O cancel out, and 0.333 times 2 is just, well, 0.666. So if I multiply that by 2 on my calculator, I get 0.666 as our answer. So our moles of H on both sides will be, 0.666 moles of hydrogen. So now that we know that, let me just erase everything. So all we have to do left is find the number of moles of oxygen in this compound. So how can we figure that out? Well, can we look at the moles of oxygen here and here in order to find the moles of oxygen in here? Well, here's the problem we have. If we find the number of moles of oxygen in carbon dioxide and water, yes, we will get the total number of moles of oxygen on both sides. But when we come to this side, or the left-hand side, we're just like, oh, wait a second. If I know the number of moles of oxygen on the left-hand side, how do I know how much belongs to this and how much belongs to this? Because the problem never tells me how much oxygen reacts. It just tells me that enough of it reacts. So, I don't know how many moles of oxygen are here and how many moles of oxygen are here. I don't know how the total number of moles of oxygen are distributed between the two. That's kind of vague. So that's why I was avoiding calculating the moles of oxygen this entire time. It was all because of the ambiguity of figuring out, how much oxygen is in each of them. And since I didn't know that, I couldn't do that. So that's a problem that many of us face. And how do we solve that? Well, there is a way. And I'll show you right now after I undo everything. So let's think about this. We know that there are 10 grams total of, this CHO compound. But we can figure out the mass of O inside the compound, or even better, the moles of O inside the compound. How can we achieve that? Well, we could think about mass composition. We know that the total mass of C, H, and O have to add up to 100% of the mass, aka 10 grams. So if we find the mass of carbon and hydrogen, then we can figure out the mass of oxygen. Since if we have the moles of C and H, then we could find the grams of C and H, and thus, subtracting from 10, we can find the grams of O. Now let me show you how that is done. So we need to find the grams of C and H, so the molar mass of C is 12.01 grams per mole. The molar mass of H, oh, that doesn't look like H, oh, now it does. The molar mass of H is 1.01 grams per mole. So let's figure this out. Well, I need to convert 0.666 moles of H into grams of H. So I would do 0.666 moles of H times the molar mass of H. So 1.01. Oh, no, that's not right. The moles go on the bottom. So moles of H, and on the top will be the mass of H. So the moles of H cancel out, and we're left with, well, let's 0.666 times 1.01. We get a mass of, let me erase this. We get a finale of 0.673 grams of H. So now let's figure out the grams of carbon. So we know that there are 0.3331 moles of carbon, and let's just multiply it by the molar mass, 12.01 grams per mole. And the moles cancel out, so we're left with grams. And what's 0.3331 times 12.01? Well, I got an answer of about 4.001 grams of carbon. So if we know the total mass of the compound and we know the mass of carbon and hydrogen, then we could definitely find the mass of oxygen. So let's just do an algebraic equation. So let me do this. 10.00 grams is our total mass, and that's equal to the mass of carbon, which is 4.001, so 4.001 grams, plus 0.673 grams, plus an unknown number of grams of oxygen, since that's what we're solving for in this problem. So let's do the math. So 4.001 plus 0.673 is 4.674 grams. And notice how there are 3 decimal places, and we're keeping true to that in our calculation. So let's just erase this and, well, leave the 4.674 behind. Now, how do we isolate this x? Well, we just have to subtract 4.674 grams from both sides. So after doing that, we know that this cancels out completely, so we could erase that, leaving, of course, the x behind. And on the left-hand side, if we subtract 10 from 4.674, we get an answer of 5.33 grams. And notice how there are 2 decimal places and 3 decimal places, so our final answer will have 2 decimal places. So now let's find the moles of oxygen from the grams of oxygen. So let's just multiply by the molar mass of oxygen. So the molar mass of oxygen is 16.00 grams per mole. And notice grams is on the bottom, so we can cancel out with the grams on the top. So we cancel those units out, and what's 5.33 divided by 16? Well, 5.33 divided by 16, it's about 0.333 moles of oxygen. So we figured out how many moles of oxygen there are, 0.333 moles of oxygen. Now that we have a ratio of the 3, atoms in the compound, we could now find the ratio between the atoms. So let me just erase all this and let's figure that out. So what we have here are the 3 different moles of each atom. So let me, figure this out. So let me draw 3 separate columns, and let me write 0.3331, 0.666, and 0.333. And these are all in moles. This is C and H and O. So now we have to divide by the smallest number in order to get a ratio. So we would divide by 0.333 for all 3 numbers. And what you come up with is that carbon is 1, and hydrogen is 2, and oxygen is 1. And note that how these are whole numbers, so I am not paying attention to the significant figures. So we have derived the ratio and thus the empirical formula for the compound, so it's CH2O. Now, we need to find the molecular formula, and we're given that the molar mass is 60.06. So we need to see how many times we have to multiply this by in order to get a molar mass of 60.06. Well, the molar mass of CH2O is just 12.01 plus 2.02 plus 16.00. And if you type that into a calculator, let's see, 12.01 plus 2.02 plus 16.00, that's actually equal to 30.03. And since our molar mass is 60.06, don't you think this is twice as much as this? So we just have to multiply this empirical formula by 2 in order to match the molar mass. So it's C2H4O2. That is our molecular formula for our answer. Now let's look at a more interesting case. The molar mass of the compound is 127 grams per mole, and they give us the percent masses for each element. So you might be thinking, shouldn't this be easy? Well, not exactly, because we have a halogen here, and we don't know what the halogen is. So let's just do this problem and see where the trouble starts. So let's assume 100 grams exactly, and that means we have 18.93 grams of carbon, 25.21 grams of oxygen, and 55.5 1.86 grams of a halogen, which I will label as X. Now, this is a problem that comes from the U.S. National Chemistry Olympiad, so naturally this problem will be a bit challenging, but with perseverance, any problem can be solved. So let's convert the grams of carbon to moles of carbon. So we know that the molar mass of carbon is 12.01, and I won't show you here because we've done it several times here, converting between grams to moles and moles to grams. So I'm just going to tell you how many moles of carbon there are. 18.93 divided by 12.01 is simply just 1.576 moles of carbon. And I'll do that for the grams of oxygen. So 25.21 divided by 16 is 1.576 moles of oxygen. So now we don't have the molar mass for the halogen, so that's where we run into trouble. So what can we do in this case? Well, we have to remember a few things. We have to remember that for any molar mass, all the elements in a compound have to at least be, in a whole number ratio, meaning that the numbers here, here, and here have to be whole numbers. So we can't have an atom that has a molar mass greater than 127 grams because the molar mass of the entire compound, including the carbon and the oxygen, is already 127. So we have to look for a halogen that has a molar mass less than 127 grams per mole, and that's because this number has to be at least 1. So I'll explain that soon. So let's take a look at our periodic table, which is right here. So let's just say that I wanted to choose the halogen astatine. So if I chose astatine for our element, then it would have a molar mass of 210. So if it had a molar mass of 210 for just one atom, don't you think that already exceeds our molar mass of 127 grams per mole? So that's why this blank spot cannot be astatine, and as a result, it can neither be, iodine, because iodine is already, 126.9, and this is 127. And the masses of the carbon and the oxygen at least take up, 10 or 20 or more grams. So we can't have iodine since 126.9 is too close to 127 grams per mole. So we have to choose a halogen from these three. We have to choose fluorine, chlorine, or bromine. So the best way to do this is just to test all three. So if we test fluorine now, so let me erase this. Let's pretend our element X is fluorine. So if we said this was fluorine, then the molar mass of fluorine, well, I can't see it. It's 19.00 rounded to the hundredths place. So 55.86 divided by 19.00 is 2.94 moles of fluorine. Now, does this make any sense? Well, let's try it out. We have to divide by, the smallest number, which is, in this case, 1.576. We would get 1, 1, and 2.94 divided by 1.576 is 1.865. So this is a really weird number. There's no way we can scale this up. We can't multiply by 10 to get, 10, 10, and 18.65 because we need whole number, ratios of elements. So as a result, this is not right because fluorine gives us a really weird, number that cannot be converted into whole number ratios. So therefore, our missing element cannot be fluorine. So let's erase fluorine and let's look at our next element, chlorine. So chlorine is another halogen, 35.45. So we are going to take 55.86 and divide by 35.45. And we get, 1.576 moles of chlorine. Now that looks right, because if we divide everything by 1.576, we simply get a 1:1:1 ratio. So at this point, I'm thinking to myself, this has to be chlorine because it just fits so perfectly. But of course, we have to be careful. We have to choose one more element. We have to try out bromine. So bromine has a molar mass of 79.90. So I'm going to take 55.86 divided by 79.90, and I get 0.699 moles of bromine. And let me just add an extra sig fig here. Alright, so if I divide everything by the smallest number, which is 0.66 or 6991, I get 1.576 divided by 0.6991. I get 2.254, 2.254, and 1. Now this is a really awkward ratio to deal with. So let's just scale it all up. So multiply by 4, because 2.25 times 4 will give us 9, which is our whole number, and this will just be 4. Now, 9 carbons and 9 oxygens already weigh more than 127 grams per mole. So as a result, this is telling me that using bromine is a bad idea. And in addition, if you think about it, 4 bromines weighs over 300 grams per mole. And that far exceeds the molar mass that we have. So this can't be right. So let's just undo everything, and let's stick with chlorine, because chlorine is the one that, just fit perfectly last time. So we're going to choose chlorine, and we know that chlorine had a 1:1:1 ratio. So we need to find the molecular formula, since this is an empirical formula. So empirical formula would be COCl. So we need to find the molar mass of this. This will just be 12.01 plus 16.00 plus 35.45. In our calculator, we get a molar mass of, 63.46 grams per mole. So how many times do I have to multiply this by to get, 127? So we have to divide 127 by this to see what, our ratio is. So 127 divided by 63.46, I get a number very close to 2. So apparently, you need 2 times the molar mass of COCl to get 127.0. So that means we have to multiply the empirical formula by 2 to get the molar mass. And we just multiply by 2. And our molecular formula will be C2O2Cl2. And that is our answer. So this was definitely a challenge, but if you have the right mindset and you know what you're doing, then you could solve any problem involving molecular and empirical formulas. So that's all for this video. I hope you learned a lot, and goodbye.